And we'll demonstrate that through some example problems, again, following those steps. So we have a good problem here. Okay. Let me draw that.
That's really bad. Do you want me to ask just in case? For clarification, but I'm pretty sure it's...
No.
The midterm is next Friday, correct?
Next Friday.
Okay.
Right.
Yes, there you go.
Did he scare you?
I thought it was Friday too, honestly.
I was like, I'm pretty sure he saw my email. Am I the only one who got that email?
Wait, did it still get moved?
Yeah.
Yeah, he moved it
Oh,
overnight. Yeah, like
so
about
I'm not crazy.
2 weeks ago.
You're the second person that's asked me, and I'm like, I'm pretty sure it's next week, but I was like, maybe
Because
skeptical.
I looked at the like schedule.
Yeah, he emailed us. You made me scared. I was like, am I the only one who got the email? I was like, am I the only one informed?
I know. This doesn't look like it, but it's kind of crooked, but it doesn't show here. My drawing doesn't do a good job because it shows that this line is continuation. So it should come a little bit further down. Here. Okay, this is better. So you have a truss like this that is loaded, and you want to find all member forces using a method of joins. Yes?
Are FE and ED supposed to be straight, but it's just a drawing, or are they?
Which one? FE and ED? No.
No,
It's kind of broken here, is not.
Okay.
Right. In fact, that's the mistake, not the mistake, the poor drawing that I did first time. Okay. So, step one was what? The method of joins. Set up your X and Y coordinates. Step two is the heart of doing truss problem for method of joins, is identify what?
The number of unknowns will be
Zero force members. And what was the criteria? You look at any joint where 3 members come together, no load acts at that joint, 2 of those are collinear, right? And then the third one, which intersect with those collinear forces, is 0. Do you see any here? Any joint that satisfies those conditions? You do, but you don't want to admit it. Yes?
The vertical joint at the far right?
What is the label? Which?
Between B and D.
Between B and D? Oh, this one you mean?
Yeah.
Oh, I didn't label. You mean C?
But there's
Yeah.
a load.
You have a force acting here, so that violates the criterion. But I still believe that there is one. Let me introduce it this way. We said if you have a joint, 3 members coming together, right? Or, in fact, we can generalize this. If you basically have a particle, right, in equilibrium, such that three forces are acting at that particle, and two of those are collinear. For this particle to be in equilibrium, this always has to be zero, right? Why? Because if you consider, for instance, this is x, this is y, and you write summation of forces about the y-axis, this would have to be zero. And you only have these two that will be equal, right? That's the concept behind zero force members. So what happened? What happens here? What do you have there? You have two forces like this. If this particle has to be in equilibrium, what happens? You said it. Okay.
X is also zero.
Sure.
Right.
There's no
So
force acting on it.
that means
It's both.
both of them are zero. Have to be zero. So if you have a joint, then yeah, because if you write summation of forces along x, summation of forces along y, this would be zero because sum of forces along y is zero. Then you end up with only one force, so that has to be zero, since summation of forces along x is zero. So if you have a joint in a truss, regardless of the geometry of these two members, where there is no load externally acting on that joint, those two members are always zero. So these two are zero force members, so you can just remove them. Now what?
Would
Yes.
B to C also be a zero force member?
No, it's-
B to C, no, but you're on the right track. C, you have two forces, and then this one, right? Since these two are collinear, so this has to be zero, right? So, in other words, this is gone. So that means that force is actually acting here, right? So that's how you simplify these truss problems, okay? And if you had actually this truss, instead of having a member like this member was acting like this, right? Then what would happen? This would be zero, right? Right? So this would be basically a force like this, holding this together. But let's consider this geometry instead of that. Doesn't matter. You're both good problems. So that truss with, I don't know how many members we eliminated, is reduced down to finding only this. So step 3 was what?
The ones with the least amount.
Identify
The least
a
amount.
joint with minimum number of unknowns. Then draw three-body diagram of that joint and apply equations of equilibrium to find all the unknowns on that joint. So in this case, you have two unknowns here. 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this is the one with minimum number of unknowns. So I will consider equilibrium of that joint, okay? And let's see, this was 2, so this is 1, so this is 1, 3, square root 10, okay? This is, okay, did I do it right? I think so, right? And this is 3, 2, So it would be square root 13. So if I write summation, if I draw the free body diagram of E, I have this force 50 Newton. I have, let's say, this force FBE, and then I have this force FEF, and that's the free body diagram, right? So I can write summation of forces. In this case, I now write summation of forces along X is equal to 0. I have FBE 3 square root 13 minus FEF times 3 over square root 10 is equal to 0. Then you write summation of forces along Y is equal to 0. You have negative FBE, okay, times 2 over square root 13 minus FEF times square root 1 over, okay, 10 plus 50 is equal to 0. If you solve these two, fortunately, I have the answer here for BE and EF. Okay, BE, okay, okay. EF comes out to be 52.7. So FB, actually EF. Okay. EF comes out to be 52.7 Newton. And since EF is moving away from the joint, that means that is in tension or compression?
Tension.
That's in tension, right? And F of BE comes out to be, and now I have 602 Newton, okay? And since that force is moving away from the joint, the corresponding member is in tension. So this one was in compression. I'm sorry, this one was in, I drew it wrong. EF is this one, so it's going away, so this is in tension. This one is going to be, BE is in compression. Okay. So we have this one and we have this one. Yes?
At least from the first drawing, the 50 Newton thing was supposed to be straight up vertical?
Right. Yes.
Yeah? Oh, okay. Must have
Yes.
just the drawing.
Right, yes. Okay. Any other questions? Okay, so now I'll go again to step 5. We go to the next joint with minimum unknowns, right? And draw free body diagram and apply again equations of equilibrium and repeat the process. So now I have what? 1, 2 unknown here, 1, 2, 3 unknown here, 1, 2, 3, 4 unknown here, 1, 2, 3, 4 unknown here. So the next one is obviously this one, right? So I would draw free body diagram of B. Force BE is a compressive force. So that means this is force BE, which is 602 Newton. Okay. I have a force of VF. Okay. And then I have this force of A, B. That's the free body diagram of that joint B. And this is 2, 3, square root 13. Okay? So if you write summation of forces along y is equal to 0, you have negative F BF plus 602 times 2 over square root 13 is equal to 0. That will give you FBF. I have the answer here. I just have to find it somewhere. Okay. FBF. Okay. Okay. BF. BD, I have GF, okay, I have BF, okay.
333.9.
How much?
333.9.
300?
334.
34, great. Okay, that's, and that is, oh, I'm sorry, this was 60.2. Well, I said 602. So this would be 33.4, right?
Yeah.
So that came out to be positive. That means this is going away from the joint, so the corresponding member would be in tension. So you write summation of forces along x is equal to 0. You have F of AB minus 60.2 times 3 over square root 13 is equal to 0. So if you could give me that number, I appreciate that. F of AB, I cannot find it here, should be 50, I think.
50.08.
50, okay, so 50. And that came out to be positive. That means the assumed direction is correct. Force is going towards the joint, so the corresponding member is in compression. So we have now this one and this one. So now this joint has 1, 2 unknowns, 1, 2, 3, 1, 2, 3, 4. So obviously this one is the next logical one to go to. So I'm going to draw the free body diagram of F. Okay? And BF, which is here, is tensile. So this is F of BF, which is 33.4. We have an applied load of 50 Newton here. We do have force of FE, okay, which is tensile also. So this is FE is 52.7, okay? And let's say this is force of GF that we need to find, and this is the force of AF. Okay. So that's it. And the slope here, this is 3 and this is 3, so this is 1, 1. So this is 45 degrees. Okay. So my drawing is not that great. So obviously you just write summation of forces along y is equal to 0. You have negative F AF square root 2 over 2 plus 50 plus 33.4 plus 52.7, and that slope of that guy was 1 over square root 13 is equal to 0, right? So F of AF comes out to be positive. Let's see, if I don't have the answer, you can give me that. I don't think I have it. Or at least I don't have it in that nice order. So if you could do that quick, would be great. How much is that?
I got,
141?
I got 140.
Oh, how much?
140.
140, should be about that. I get 141, but that's okay. I just found it. So that's, again, positive. That means force going towards the joint. So the corresponding member would be in compression or tension? Compression. Okay. Now summation of forces along X is equal to 0. I have negative FGF plus 141 square root 2 over 2 plus 52.7, and that is 3 over square root 13 is equal to 0. So FGF comes out, let's see if I have that here.
Isn't that root 10?
Is it root 10? Which one?
Yeah.
Oh, I'm looking at it from there, that's why, okay.
Yeah, so when I recalculated it with
That's
root
your
10, I get 141.5.
Oh, okay, so you got it right. So is this correct or not?
It's 141.5.
Oh, 141.5. Oh, okay. So let's see. Okay, so that's good. Okay, so how much is this one? I don't think I have it here. GF, is that GF? Yeah, I have that. It's 150. Is that right? Is that what you get?
Yeah, I get 149.6.
Oh, okay, so 150. And it came out to be positive. That means assumed direction is correct. Force is moving away from the joint, so the corresponding member is in tension. So we have this one, and we have this one, right? So we have 1, 2, 3 here, 1, 2 here. So this is easier, right? This is the next logical choice, I mean, not because of just easier. That is, according to the procedure we discussed, that would be the next choice. So force AF, which is what we found, is compressive. So this is force AF, okay, which is 141.5 force AF, and this was 45 degrees. Okay, that's, we are drawing the free body diagram of that. So this is A, and force AB, okay, is compressive, is a compressive force. So this is 50 Newton, force FAB. So the one that we are looking at is this one, force of AG. Okay? So just write summation of forces along Y is equal to 0. Okay? So you have negative FAG, okay, plus 141.5 times the square root of, let me make sure that is, okay, that's actually square root 2 over 2, right? Okay? Is equal to 0, right? So this would be FAG, how much?
100.
How much?
100.
100, that's correct. And it is positive, so the assumed direction is right. Force is moving away from the joint, so this is in tension. Okay? So we found this one. So as you can see, and as I had promised, in frames you had one free body diagram that you didn't use. One member forces. In trusses, you always end up with one joint that you did not use. And we did not use this. Okay? If you want to verify your answers, you need to find all the external forces, right? And then check all those numbers against the equilibrium of this joint. But in my advice, if you're asked to find member forces, you do not have to find the reaction forces. You don't have to. If you follow these steps, start with the minimum number of unknowns, joint with minimum number of unknowns. And the problem is statically determinate. That is, you only have 3 unknown external support forces. You do not have to find those reaction forces. In fact, it's easier most of the time. Okay? You have a question?
I think that kind of answered it.
Oh, okay.
I was going to ask about why that external force at A isn't creating an X and Y.
I see. Yeah, those just are all there, right. Any other questions? I'm going to do one more problem. So for some reason, we are a little bit ahead in this section. So that was a good problem. Let me do actually another problem which I didn't do in the other sections. That's better. Okay. So through this problem, I want to not show you a new concept, but something again that if you remember that makes your life easier. Let's put it that way. I always like to make your life easier. Okay. So this is a problem that we have. In fact, it is, if I'm not mistaken, it is a problem from your own textbook, but that is a good problem. 8A, this is 6 and 2. Okay, so we have 4 A's. Okay, 1, 2, 3, then we have point here, 6. This is 6. Okay. Okay, we have a roof truss that is loaded like this. Okay, this is. Let me label these A, B, C, D, E, F, G, H. Oh, no, we need the dimensions here. This is so again, this is a truss that we want to find all member forces using the method of joints. Okay. Before I do the problem, let me show you or present at least a basic concept that helps you in saving time in doing truss problems. Anytime you have a structure that has a line of symmetry, which in this case you can see that easily. This is a line of symmetry, okay? And the loads are symmetric with respect to that line of symmetry. All members that are symmetric with respect to that line carry the same force. So you only have to solve for half the problem, or half the number of members. What I mean is, this member has the same force as this one. This has the same force as this one. This has the same force as this one. This has the same force as this one, and so on. So members that are symmetric, yes?
Does it matter that like A and E are connected to the ground or whatever differently?
No, it doesn't. It does not. Good question. Any other questions? Yes.
So you can look at this and immediately say that the support at E doesn't have an X component.
That is correct, yes. Support at E has no X component because all the applied loads are vertical. Like that brings me to the next point. So all these forces are symmetric, right? And then when it comes to the supports, if again the load is symmetric with respect to the line of symmetry, okay? If you write summation of forces along Y, that would automatically tell you that half the load goes here, half the load goes here. So you really don't have to write the equation of equilibrium, because you can quickly see that half the load goes to each side. So then you have what, 1,800 and 600, 2,400. So this is the reaction force is 1,200 here and 1,200 pounds here. So when you have a line of symmetry, take advantage of that. Don't do too much work that is not necessary. So let's come back to this again. I'm not going to write down this step. By now you know that. One is XY, two is, these are the first two most important steps, identifying zero force members. Do we have any zero force member here?
HB and FB.
BH, yes, zero force member because it's a joint, two members, collinear, no external load. This one goes, this one goes, right? Any more? No. Okay, so I'm just going to ignore this half of the truss and concentrate only on this half. So I have 1, 2, 3, 4, 5 members to basically find. And you start with a joint with minimum number of unknowns. Since in this case, it was so easy to find the external support, yes?
Where did you get that 1,200 pounds?
See, as I said, if it is symmetric with respect to the line of symmetry, loads are symmetric, half the total applied load goes here, half the applied load goes here. So if you add these up, it would be 2,400 pounds. So 1,200 goes here, 1,200 goes here. So in this case, it's so easy to find the external reaction force. So you start with the joint with minimum number of unknowns, and that, you see, would be this joint, right? So let's consider the free body diagram A, and let's see what these slopes are. This is 6, this is 8, or 3 and 4. So this is 5. So AB, assuming force of AB is like that, this is 3, this is 4, this is 5, this is 1,200 pounds, and then this is 300 pounds. And then you have force of AG, or I would get rid of this because it doesn't exist. So that's the force of AG, right? So you just write summation of forces along Y is equal to 0. You have negative 3/5 of FAB, okay, plus 1,200 minus 300 is equal to 0. So this is 900, or it would be 300, okay? So that'll be F of FAB would be 1,500 pounds, if I did not make a mistake. Okay? Which I don't think I did. So it came out to be positive. That means the assumed direction is right. That since the force coming towards the joint, the corresponding member will be in compression. Yes. Now, next one, summation of forces along y is equal to 0. I'm sorry, the x is equal to 0. So you have FAG, okay, minus 4/5 of FAB, which is 1,500, okay, is equal to 0. So FAG is 1,200. Force is moving away from the joint. That means the corresponding member is in tension. Yes. So you already found forces in this and in this, right? So at this joint, although these two are equal, still you don't have either of one. So you have 1, 2, in a way 3, you don't have them, right? So I'm going to use this one because I have 1, 2 unknowns, and it's easier to find. So let's look at joint B, okay? You have the force of AB, which we found, and that one was compressive. So this is force AB, which is 1,500, and this one was 345. So that is joint B. You have an applied load of 600 pounds. Then you have this one. Let's look at the slope of this guy. This is 2, this is 8. So this is 1, this is 4, so this is square root 17. And this one is 8 and 6, so it would be 4, 3, 5. Okay, so this one, I assume it is acting that way. Force of B, G, this is 3, 4, 5, and then I have this force, which I don't know, that's something I want to find. That is the force of B, C, and this is the one that has 1, 4, square root 17. So that is a free body diagram of joint B. Okay, so obviously, as you can see if I write some of forces along X and B, you get 2 equations and 2 unknowns, and you solve for those 2 unknowns. So let's just set up the equations. So let's summation of forces along X is equal to 0. That will give me 4/5 of 1,500 for this, minus 4/5 of FBG, okay, minus 4 over square root 17 of FBC is equal to 0. The right summation of forces along Y is equal to 0. You have negative 600. You have plus 3/5 of 1,500. You have 3/5 of FBG, and you have negative, okay, 1 over square root 17 FBC is equal to 0. Okay, too much to ask you to do it, right? Is not? You double check that. I may have that. here, let me see. I might, don't guarantee it. AG, where is AG?
We resolved for AG.
I have AG there?
We resolved for
I
AG.
have that, right, so I had. So I think I'm going to rely on you to give me those numbers. I can simplify it at least a little bit because this is going, so I have F, B, G, okay, 0.2 plus 1 over square root of 17, F, B, C is equal to, okay, 300, this is equation 1. I'm not sure if that helps. I'll trust your answers.
I don't know if I trust mine.
That's okay. We'll be
I
an
got,
answer.
I got x is equal to 0 and y is equal to,
So FPG and F,
yeah, sorry, so, FBG was equal to 0 and FBC was equal to, 1236 for 34.
1234. I think with FPG, in fact, you're right. I have also 0 here. For some reason, it came out to be 0. And FPG, right, it just happened to be 0. It's not a zero force member. Because of those numbers, it came out to be 0. So do not lose your trust in me about that criteria, okay? It's just an accident that this one came out to be positive. Assumed direction is right. So FPC then, right, this guy, that means where's the free body diagram? Here's BC going toward the joint, so the corresponding member is the compression. Okay, all right. So we found this guy, and we found this guy, and in fact, we are almost done, because if you look at the free body diagram of this guy, this force and this force are the same. Somebody, yes?
So we found 0 there. If we'd forgotten to take out one of the 0 force members, we would have just found 0 for that one as well.
Oh, if you forgot to take these one out,
Yeah.
your life would be miserable. Because you have 3 more operations.
Okay.
Right, yes. Yes.
But also, how do you like do it so fast, like with the calculator?
She's fast. What do you think?
Is there some way like I don't
You
know?
plug
Some calculators you can.
Some
plug in
calculate, I don't know.
handles
She's
all
fast.
the way
I'm
up.
not gonna question anything.
Did you use the matrix?
Yeah.
Oh, you have it,
Yeah.
equation solver? Great, okay.
Oh, I
See, you guys are ahead of us. Like in the old days, I had to use Cramer's rule, do all these long-term solutions. I'll tell you a story, we have time, so I'll tell you the story. So you go to, then this one, right?
They just have
Now, if you draw the free body diagram of
calculation.
G, okay, FBC, and I'm sorry, BG is 0. So if this came out to be 0, right, and this is 0, so that makes it very easy, right? Because you have, okay, only this force, these forces, you have them, right? And there's no applied load here. You have, okay, you have this force here, right? So what happens there? If you draw the free body diagram of this guy, what happens?
It's 0 force.
Comes 0, yes. Because there's nothing here, right? And again, just an accident. Yes.
So I know that it would be like a total pain in the butt if you didn't remove the 0 force members, but is it like in equilibrium problems if you don't identify a two-force member, there's too many unknowns? Is it still
Yeah,
possible to
just-
solve this
It's
problem?
still possible to solve it,
It's just, it's a
absolutely.
lot harder.
It's just
Okay.
gonna take much longer.
Okay.
Yeah, exactly. That's why I always emphasize, find the zero force members first, right?
But if you forget one, you can
Yeah,
still get the correct.
you still can just go ahead, use all joints, equilibrium, all joints, and you have a lot of equations and whatnot, but you can still do it, okay? All right, good, so we have 30 seconds, so I'm gonna tell you this story, okay? A colleague of mine, this is way back, when just these search engines had started and people were creating some fun stuff on the web. A colleague of mine was teaching fluid mechanics. So he had given a problem that had something like this, f of x dx, okay? And something like that. So students, of course, they come and, some students come and ask him, okay, what is the unit for dx? Okay, but long story short, he retook the course. Next time, he couldn't do any integral. And then the next time he takes the course, makes an A in the course. So this colleague was curious, said, how did you do that? How did you solve all these sophisticated integrals? Even on integral.com. That's what. So my point is this, these tools have made the life a lot easier now, right?
Even on integral,
Right?